a salt crystal here. The water molecules here. So what's happening is salt crystals starting to dissolve in water. So we want to know what happens when the salt crystal dissolves in water. You know, does it form molecules? That is, molecules of sodium chloride. But if you look, it doesn't form any molecules here. What's happening is, well, here's a molecule, but it doesn't last that long. Eventually, do you see that break apart? Okay, then it came back together. Well, we don't really call that molecule. We just call it an ion pair. Well, there's a lot of molecular dynamics. Sodium chloride is a very common one. And so what happens when sodium chloride dissolves in water? Here's one that doesn't show the water molecules. It just shows the sodium chloride. What happens is the salt crystal breaks apart. It breaks apart into individual ions, not molecules. If it broke apart into molecules, then we'd call it a molecular solid, you know, and the molecules would be intact and distinct units. And so there's lots of simulations of dissolving sodium chloride in water. There's another one. Lots of different music, but here you can see the ions are breaking apart. And what happens is the waters will collide with the ions, and the waters are actually attracted to the ions because of the electrical attraction is there.
Chloride ion.
See, this one has some audio. Actually, I think we saw this.
Are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions.
So these are all electrical attractions here.
The crystal dissociates into solution.
All right, this is different than...
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution.
All right, so what happens with the salt is this. Salts, they're going to break up into the ions here versus breaking up into molecules. There's no NaCl molecules here. Whereas if we have something that forms molecules, you know, typical salts are metals and nonmetals, so we know that. There are some exceptions. Something like ammonium chloride would do the same thing, except the ammoniums would break off intact. The chlorides would break off, so this might be an ammonium here that would break off. The ammonium itself shouldn't break apart. But anyway, when we have an ionic solid or ionic lattice or lattice type structure, this is typically what we expect to happen. If we have something else, like a dissolution of sugar, it's going to look different because sugar forms molecules. So a dissolution into molecular dynamics. Molecular dynamics is just these theoretical calculations. Different than a molecular. So, for example, we can just do it as a cartoon sketch here. sugar. Sugar forms a molecule. This sugar molecule is going to be, for sucrose, C12H22O11. That would be its formula. You have quite a big structure to it. But these sugar molecules themselves are held together in the solid by electrical attractions. These electrical attractions are just weak compared to actual bonds. Those are actual bonds holding the lattice together here. And so sugar shares characteristics of all molecular solids. Low melting point, low boiling point. Although you try to melt sugar, you might cause it to oxidize instead of melt. And so you might have a chemical reaction occur. If you try to boil it, it's going to be tough to boil. So some things decompose before they melt. And so when you look up melting point, if you see a D there, that's the decomposition temperature. Rather than melting, it'll probably burn or something like that. But anyway, they're soft, compared to salts. And so we have sugar like this. Now the water comes along, and the water does the same thing. It's going to tug and pull and collide with the sugar water molecules themselves and surround it. Sugar is quite soluble in water. And so these come off as intact sugar molecules. So when they come out intact, we'll have a sugar molecule surrounded by water molecules here. So the water molecules, which I'll just show like this, the water molecules here. Like that. And so we got to know this. Okay. What we think about is when something dissolves, does it break apart into like individual atoms or ions, or does it stay together, as molecules here? That topic is something called electrolyte properties. Let me take a look at that here. Bring this We're not done with chapter 8 yet. I want to talk about this. Okay. This is a light bulb conductivity apparatus. Is this just the figures? What is that used for? Well, that's a simple test to see, when it dissolves in water, what happens. And so if we look at ethanol, ethanol is a liquid, pure ethanol. And so liquid would have a whole bunch of these ethanol molecules, held together by electrical forces, attraction. And so we have ethanol liquid. Ethanol is very soluble in water. Ethanol is very soluble in water because it's light dissolves light. And so do you see this portion of the ethanol molecule is very similar to the water molecule here. And so light dissolves light, but this part is not. You look at this is hydrocarbon or oil light. Carbon and hydrogen species are called hydrocarbons. And so as long as this is not too big, then it's okay. So methanol is very water-like. Ethanol is very water-like. Propanol is very water-like. But when you get to butanol has how many carbons? Okay, meth has how many carbons? 1. Eth has 2. Prop has. But has 4. When you have 4 carbons, what happens is this part grows bigger. This gray and white part grows bigger. Is that water-like? No, that's not water-like. That's oil-like. And so when you get to butanol is not soluble in water. Whereas ethanol, methanol, propanol are quite soluble. And so it depends on how big this part grows. It becomes less water-like. But that's the solubility rules that we learn for molecular. For molecular compounds, you're looking for, does anybody remember the rule? It's one sentence rule for molecular compounds. Molecular compounds the solubility rules would be, well, the solubility rule is well, somebody asked me, I don't know who, but somebody asked me, if you want to do extra stuff for studying, if you have time, what you should do is you should make sure that, you review notes. Light dissolves blank. That should be written in your notes, and if you read it, if you read it like 5 times, you're way better off than just reading it once and forgetting about it, And so, light dissolves light is this. This is very simple. So what we're looking at is light in terms of structure. So this ethanol is like water in this red and white part here. So it's very similar. Now, there are other things like methane. Is methane similar? No, methane's going to it's not going to have this red and white part. It's just going to be gray and white. When you look at methane, does methane look water-like at all? No, methane's just going to bubble right out. And so, hydrocarbons, yeah, I know. But anyway, that's we'll talk more about when we get to structures and molecular compounds later. We'll look at that. Right now, we're just looking at ionic and molecular and what happens when they dissolve. So, is ethanol soluble in water? Yeah. When ethanol dissolves in water, the question we ask is, does it stay together as molecules or does it break apart into ions? And the thing is, if it's an ionic compound, we expect it to break apart into ions. If it's a molecular compound, we don't expect it to break apart. And so when ethanol dissolves in water, it stays as molecules here. And so we'll just have ethanol and water mixed together. This is a homogeneous mixture. You can see here, it's very homogeneous. Okay, now one thing about ions is they have a charge. And if we have mobile charges, that is charges that have translational motion, then we can conduct electricity. And so here we have mobile molecules, but none of these have a charge, so they don't conduct electricity. And so what we have here is we have a hot wire coming in here, and electricity should flow through this, but what we see is there's no electricity flowing through this solution. The reason why water, a lot of people say water and electricity don't mix, right? However, if it's DI water or distilled water, does distilled water conduct electricity? No, it doesn't. Tap water conducts electricity, but distilled water does not really conduct electricity. In fact, what we call a resistor. Insulator, not a resistor, an insulator. And so here, this is pretty pure. There's no dissolved minerals in here. If we have dissolved minerals, like say there's some copper 2 chloride in there, then this is going to conduct electricity. Why does it conduct electricity? Because copper 2 chloride, which is, what kind of structure is that? That's a lattice structure of ions, right? When this dissolves, it's going to split up into the ions. So here we have chloride ion, here copper 2 ions. Copper 2 ions are a lot smaller than chlorides, you can see here. In general, cations are smaller than anions. There's only 1 or 2 or 3 exceptions. So cations are always small compared to anions. All right, so that's for monatomic. For polyatomic, of course, it varies how many atoms there are. But something like this conducts electricity quite well. If it conducts electricity quite well, we call it a strong electrolyte. If it doesn't conduct electricity at all, we call it non-electrolyte. And so electrolyte properties depend on how well it conducts electricity. But it turns out there are 2 definitions of electrolyte. One definition is based on how well it conducts electricity. The other definition is based on, does it split up into ions or does it not split up into ions? In this case, it splits up into ions 100%. And in this case, it does not split up into ions 100%. But we have these borderline things that are borderline molecular, borderline ionic. And those are acids like this. Like the strong acids are not borderline, but the weak acids are. The weak acids are kind of borderline between ionic and molecular. And so if we have a weak acid like acetic acid, what happens is some of it splits up. Some of it stays together. It's a weak acid. So weak acids aren't the greatest proton donors. However, strong acids are excellent proton donors. So if we had a strong acid like HCl, it would conduct electricity very well here, because HCl can lose its proton quite easily, H+, and Cl- would be the ions here. Over here, if we have a weak acid, then some of these stay together. This is an acetic acid molecule, and some of these break apart. This would be an acetic acid missing the H. You see here, it's missing the H+, it's over here. And so here's the acetate ion, C2H3O2-, and here's the H+ ion. And these ions can conduct electricity. Well, only about in acetic acid, only about 1% of the molecules split up. So out of every 100, 99 don't, and 1 does. And so here's one that's split up, and there should be about 99 that aren't split up. Yeah. It's actually less than 1%. And so, but that small concentration of ions will conduct electricity here. If you see the light bulb is a lot dimmer, it's a lot dimmer because there's a lot fewer ions. And so the two ways of defining electrolytes, and it's a bit tricky. One, a strong electrolyte is going to conduct electricity well. A weak electrolyte doesn't conduct as well, and a non-electrolyte doesn't conduct. If you're an electrochemist, that's how you do it. But we're going to use a different definition. Our definition is going to be this. Our definition is strong electrolytes dissociate into ions about 100% or 100%. Weak electrolytes partially dissociate, and so most of these stay intact, and some of these dissociate into ions. And non-electrolytes do not dissociate at all. And so we're going to get some practice recognizing. How can you recognize when you have a weak, a strong, or non-electrolyte? Well, one, you could stick a light bulb in there and see the light that does it. We don't have to have the electrodes touch, as long as they, the electrodes aren't touching here, so there's a big gap. It's only if the solution conducts electricity here. So here's an example of a strong, weak, or a non-electrolyte. What would you? This is a strong electrolyte. In fact, this is a solution, an ionic solution, which contains potassium ions and chloride ions. And so this is KCl, potassium chloride dissolved in water. Now, when we hook up a battery or we plug this into the wall, what's going to happen is there's going to be electrons pushed this way. So this is going to make this piece of metal negative, and it's going to withdraw electrons from this piece of metal. So it's going to create what's called an electric field. And so the negative ions are going to be attracted here, the positive ions are going to be attracted here. And that's going to create electric current. And so this can conduct electricity here. This is how tap water conducts electricity. Movement of the ions conducts the electricity with charge. Well, here, potassium chloride is what we call a strong electrolyte. One, the bulb is brightly lit. And two, the ions dissociate completely. But it depends on the concentration. So, for example, the more concentrated, the better the conductivity. The less concentrated, the lower the conductivity. It just depends on how many ions you have. So if you cut the concentration in half here, it's going to conduct electricity not as well, less effectively. And so what it depends on is how brightly this bulb lights up depends on the concentration. And so what we have to do is we have to compare things of equal concentration that is fairly concentrated. Otherwise, what could happen here is that you could have potassium chloride, which should conduct very well, but it's extremely dilute. If it's extremely dilute, that is, you get rid of most of these ions and you just have very few ions in solution, then it's not going to conduct electricity very well. You might mistake it for a weak electrolyte. And so this is why we're only going to look at one definition. The one definition is, for fairly concentrated solutions, we expect the light bulb to light up brightly. But of course, we might have dilute concentrations. And, the light bulb. And in fact, if you keep diluting it and adding more and more water, it's going to get dimmer and dimmer and dimmer, even though you have a strong, what we call a strong electrolyte in there. And so this is the definition. So we're going to ignore the other definition about electrical conductivity until you get to maybe Chem 1A. But for this is how we define it. Strong electrolyte, substances that when dissolved yields a solution that is a good conductor of electricity because of nearly complete ionization or dissociation. Well, then that screws everything up because this is a composite definition. Sorry, this is not a good definition because of this. Is sodium chloride a good, strong electrolyte? Well, sodium chloride, when it dissolves, breaks up into ions, right, and should conduct electricity, right? That is if it's concentrated. But if the sodium chloride is very dilute, is it going to conduct electricity very well? No. And so then you run into the problem. Well, at what concentration do you stop calling it a strong electrolyte? Because let's say at 1 molar, well actually you don't know the concentrations yet, but let's say if it's fairly concentrated, no problem, but as it gets more and more dilute, then we have to stop calling sodium chloride a strong electrolyte. Well, that presents a problem because we want to know, is sodium chloride a strong electrolyte or non-electrolyte or weak electrolyte? And therefore we're going to ignore this. We're going to ignore the good conductor. It might not be a good conductor because it might not be concentrated enough to be a good conductor. And so we're going to focus on the second definition. The second definition is complete ionization or near complete ionization. Ionization means it breaks up into ions. Dissociation means it breaks up into ions. And so ionization, dissociation is the same thing. It breaks up into ions. And so we're just going to focus on the second definition because we're just going to call, hey, sodium chloride is a good electrolyte. It doesn't mean it's going to conduct electricity really well. You got to make sure it's fairly concentrated to conduct electricity. But it's a good electrolyte because it has near complete ionization or dissociation in the solution. Weak electrolytes are a weak conductor of electricity. Well, you could have a very dilute strong electrolyte will be a weak conductor of electricity. And so we've got to avoid that definition. We're going to focus on this definition. Limited ionization or dissociation. And so acetic acid would be a perfect example of a weak electrolyte because only a fraction of the molecules dissociate into ions. Most of the molecules stay together. A few ions break apart. A few molecules break apart into ions. Non-electrolytes are substances that do not dissociate. Again, this is confusing because, if your sodium chloride is very, very dilute, it's going to appear to be a non-electrolyte, but that's not the case. And we're going to call sodium chloride a strong electrolyte. So the definition here, we need to change it. The definition we need to change here is that it's the substances that do not dissociate. And so the difference is this: strong electrolyte, complete dissociation; weak electrolyte, partial dissociation; non-electrolyte, no dissociation. That's the way. And the conductivity depends on concentration. So I'd like to break things up. Okay, but before we do that, let's talk about how to identify this. Let me go through it. We can identify which compounds are going to be strong, weak, or not by just looking at the patterns. Let's see here. So you know what? So I don't have the. I have to get a pen. All right, so strong electrolytes, how to identify? Well, how to identify, these are the strong acids. All strong acids are strong electrolytes. Do you know the 7 common strong acids? Well, if you're looking for stuff to do, you should memorize them. Somebody tell me what the 7 common strong acids are.
Hydrochloric acid.
Alright, hydrochloric. Okay.
Hydrobromic.
Alright. So basically what alright, we'll do hydrochloric, hydrobromic. Just tell me the formula. It's HBr, HI, HF,
HNO3.
HNO3. HF is not there.
H2SO.
H2SO4, which is called what?
Sulfuric acid.
Sulfuric. So 5. HClO4. HClO4, which is called perchloric acid. That's 6. HClO3. That's 7. So this is 7. So if somebody's looking for something to do, memorize those. It's a good thing to do. Sure. So these are the 7. So what do the 7 strong acids do? The 7 strong acids, when they're dissolved in water, we don't expect to find molecules. When they're dissolved in water, well, what do we expect to find? We expect to find all ions, even though these look like molecular compounds, because we expect to find all ions basically because let's do that. So what's going to happen with the strong acids is this. If I have HCl in water, I think I'm still subscript mode here. Entirely or near entirely of what? H plus and Cl minus. Okay, now we say that okay, HCl in water consists of H plus and chloride dissolved in water. That's it. And so the same goes for all these up here. The strong acids are one. What else do we have? What else we have are the strong bases. Let's see if I can get this. Go down one level. This is right there. Strong bases. What are the strong bases? Strong bases you don't have to memorize, but you should know a couple of them at least. CH3 minus. We'll skip that one. That one's not that common. Let's do NH2. NH2 minus. What's it called? O2 minus. OH minus. All right, I have to write this down here. Strong bases, hydrolyzed water. Let me talk about what hydrolysis is. Hydrolyzed water completely. What that means is it reacts with water. And so, for example, if I take NH2 minus plus H2O, I'll fix this, maybe I'll fix this H2O. What happens here is that the NH2 minus is too powerful of a base, and it'll attack water. If the NH2 minus attacks water, bases, they want to take a proton. Water doesn't want to lose its proton, but NH2 is too strong. So if NH2 minus takes a proton, what does it form? It forms NH3. And then water is left as what? OH minus. So this is what happens here. Strong bases hydrolyze water. And so this is too strong of a base to exist in water. It'll attack it. It'll form hydroxide. Hydroxide is the strongest base that can exist in water stably. This is why. Did you notice on your chart here? The chart. Did you see here? These lines here. This is a dividing line. All of these bases up to this point can exist until we hit here. Once we hit here, then this is the limit. This is the limit because all these bases down here are so powerful, they'll attack water completely. And so sulfide's the same, amide, oxide, hydride, methide, all these will attack water. When they attack water, we call that hydrolysis or hydrolyze, and we get a hydrolysis reaction. Hydrolysis means breaking apart the water. So this NH2 minus. All right, now we got to put in the states here. This is aqueous, this is liquid, this is aqueous. Ammonia is very water-like, so it dissolves. This is aqueous. Sulfide I should add here. This is 7.12. And so what happens with sulfide? You tell me. Let's do it. If sulfide is dissolved in water, then we know that sulfide is too strong to exist in water. So we'll do one more example here. So what happens when sulfide is dissolved in water? What results? Tell me. HS. Is there a charge on HS? HS minus. Plus. Hydroxide. Yeah, that's exactly what happens. Sulfide is too powerful. And so sulfide is going to attack the water to form HS minus and form hydroxide. Which is the strongest base that can exist in water? Hydroxide. And so all the strong bases are equalized in water. All the strong bases are equalized in water. That means this. Even though methide is the most powerful, sulfide is plenty strong enough to completely react with water. Methide, yes, it is more powerful. So it's going to have an easier time stripping the hydrogen off, but once it's completely reacted, that's it. And so the interesting thing about all these is this. There's something called the leveling effect. The leveling effect is that all these bases have the same strength in water because all of them yield the strongest base that can exist in water, which is hydroxide. And so all of these bases attack water to produce hydroxide, except one of these is a little bit stronger. The rest are the same. Which one is a little different? One of these I would not classify the same as the others. Do you know which one? Because all these will attack. Well, they're all slightly different, but there's one that's definitely going to be different, and that's oxide. What's special about oxide? Well, replace, did you write that down, the sulfide reaction? Replace sulfide with oxide, and what do you get? You get not one, but 2 OH minuses. And so you get double the amount of hydroxide. Well, double the amount of hydroxide is different. And so this is why it's different than the others. But the others are all going to produce 1 hydroxide for every one of these. Oxide will produce 2 hydroxide for every one of these. So it's a little bit different. But that's called the leveling effect. Now, weak bases are not that strong. You know, all these are plenty strong to attack 100%, but weak bases aren't. And so weak bases will get into a tug of war with water, and water is going to be able to fend off the weak base to different degrees. So you have a tug of war for the proton between sulfide and water. Sulfide's going to win completely. But if you get a tug of war between phosphate and water, well, phosphate's stronger, but water can fight and keep some of its protons. And so what we have for weak bases is we have what's called partial hydrolysis. For phosphate, it's like 25%, 25%, I think, or so. 25+% of them are successful in taking the hydrogen off water. 75% are going to be unsuccessful at any given time. This is molecular dynamics, so it's always changing, who the player is, whatever. Now it gets worse, as it gets weaker and weaker, then it becomes worse and worse. And so when you get to something like fluoride, or let's stop at acetate. Acetate here, this base is so weak that only about 1% of these will be successful at taking a proton of hydrogen. The other 99% won't. And that 1% changes because of molecular dynamics, the collisions, things revert back, and this kind of stuff. And so here, going one, and this is going to be way less than 1%. We're going to be successful. And so, this is about the most, which is about 25% success. These are 100% successful. And so we have different degrees of bases. And so the weak bases do what we call partially hydrolyzed water. These guys up here are too weak. These guys don't hydrolyze water at all. These guys are 0% successful at hydrolyzing water. Here. Now, the same thing holds for acids. Do you know what the strongest acid that can exist in water is? The strongest base that can exist in water is hydroxide. What's the strongest acid that can exist in water? Hydronium. Do you see the dividing line here? These acids here are too strong. These acids are going to attack water. When an acid attacks water, that's called hydrolysis too. It doesn't have to be a base, but they do different things. When an acid attacks water, it gives water its proton. and ends up forming hydronium. And so if you have HCl and water, we end up forming hydronium and chloride. We end up not forming hydrogen ions. This slide is wrong. This slide is totally wrong because of the sizes. You know, acetate's kind of big, water is about this. This is kind of accurate, this is space filling. But this is totally wrong about the size of a hydrogen ion. Totally wrong. Why? A hydrogen ion is way smaller than this because a hydrogen ion is just a single proton. A single proton's not that big. You know, the proton's like the nucleus. The nucleus of an atom is tiny. The comparison was if the nucleus was a ping pong ball, then the atom would be like a couple of football fields, something like that, right? And so here we're looking at something that's way too big. Well, if this is the hydrogen atom, that would be a couple of football fields, and then the nucleus should be a ping pong ball. So if this were a couple of football fields, then that dot would be extremely small, right? Well, obviously they're going to make it over exaggerated in terms of size because so we can see it. But what that does is it means that a single proton is very unstable electrically. You know, like a high voltage. You know, if you take a whole bunch of electrons and then concentrate them, you know, you're going to create something called a high voltage. Versus if you take a whole bunch of electrons and spread them out, then you're going to create a lower voltage. And so this is like creating a very high voltage because we're taking a positive charge and concentrating it. And the smaller the point you concentrate it, the higher the voltage that becomes. And so if we take that positive charge and spread it out over a big ion, like potassium, then we're going to create a lot lower voltage. So let's take a look at a big ion like potassium. This is a big ion, potassium. It has the same charge, it's spread out over a much larger volume. I talked about this during the first week. What did I call it? Does anybody recall what I called that? What? Called the spreading out of the charge. I'm just explaining it a different way this time versus earlier. The spreading out of the charge, or the concentration of the charge. The charge to size ratio. I called it something, but I gave it a name. Well, you know, this concentrating of charge, the charge density. Charge density is something we're very interested in. The more concentrated, the higher the charge density. The more spread out, the lower the charge density. Charge density is related to the voltage. So the more spread out it is, the lower the voltage. So it's also related to reactivity. Well, it turns out that single protons are too reactive to exist like this. If we have a single proton here, it's going to attack the water immediately. When it attacks the water, it looks for negative. This red is negative charge density, so it attacks that. When it attacks that, it forms hydronium, H3O+. We'll talk more about that when we get to acids, so don't worry about it right now. We're going to get to acids. There's a chapter on acids. We'll talk about that at that time. Okay, strong bases hydrolyze water completely. when I say H plus here, I should change that. And so let me edit this slide a little bit, because this H plus is really what? I need to put this in quotation marks, because it doesn't really exist as a single proton. What does it exist as? This is really, the proton's going to attack water, so it's really H3O plus, or hydronium. But H3O plus is such a hassle to write. You know, it's just easier just to dissociate these into ions and not worry about the proton attacking water. But the proton, like this, won't exist. It's going to attack water to form hydronium. Again, hydronium is too much writing, so we usually leave it as H plus in the table. Otherwise, it takes up too much space. But chemists, a lot of things go unwritten. They're just assumed you know. You're in the know. Well, that presents a problem, because sometimes people are not in the know, but they don't know. All right, there's one more thing that so I'm not good at editing these PowerPoints. Yeah, I'm not a PowerPoint person, but strong acids are strong electrolytes. Strong bases are strong electrolytes. There's one more thing that are strong electrolytes. And, soluble salt. Strong electrolyte. So soluble salts would be like sodium chloride. One, I like to divide it into two things. One, if I take a look at sodium chloride, which is normally solid, the first thing I ask myself is it soluble? And it is soluble. It's a sodium salt. Sodium salts are soluble. And so that means it dissolves in water, basically. And then I ask myself, is it a strong electrolyte? And it is. So it splits up into ions. Na plus, AQ, plus, Cl minus, AQ. And so all the soluble salts are assumed to split up completely into ions like that. And so the first arrow indicates that there should be water above this. It's asking, is it soluble? Yes, sodium chloride is soluble, so we dissolve it in water. When it is dissolved in water, the second arrow is asking about what we call electrolyte properties. Electrolyte properties are, does it break up completely, partially, or not at all? That's all. So this is electrolyte properties. Does it break up? Yeah. Completely? Yes. Completely. All right. That's a strong electrolyte. So let's take a look at the weak electrolyte. Can you guys see this okay? What are the weak electrolytes? The weak electrolytes, we can identify these. These are the weak acids. Weak acids. Well, how do you know what the weak acids are? Well, how do you know what the weak acids are is if it is not strong, then assume that it is weak. And so we recognize an acid because all acids have the same cation. What is the cation in the acid? Hydrogen. And so we can have any exotic acid here. Let's say H3ASO4. H3ASO4, is that a strong acid or is that a weak acid? That's got to be a weak acid because that's not one of the 7 strong ones that I've memorized. Do you know the name of that acid? Arsenic acid, yeah. And so what this means is that weak acids only partially break up. And so what we have is a bit more tricky of a situation. Acids are soluble. And so what this means is that the solution of this is mostly H3ASO4 and a little bit what a little bit is, we have to define that. H3ASO4 in water forms a little bit of ions, but stays mostly as intact molecule. So H3ASO4 forms a molecular structure, whatever, if it's solid or if it's liquid, or even if it's gas, it consists of independent molecules. When you dissolve that in water, it still stays as independent molecules. A few of those will break apart and be attacked by water. Water is an acid or a base. Water is interesting because it can attack acids and it can attack bases, but H3ASO4 is difficult for water to attack. Or another way of thinking about it is H3ASO4 is difficult to attack water. It's not soluble. Normally, when we think about acid-base reactivity, we think in terms of the base attacking the acid. The base is trying to take that hydrogen away. And so is the base strong enough? Well, water is a base. Is it strong enough? No, it's not strong enough. Water can only partially dissociate this. But there's different ways of representing this in equation form. And I can't do that here. Maybe I can do that here. I have some smart art. I just need to draw a line. Draw a line. This is what some people end up doing is they'll draw uneven arrows like this. And then this goes to ions, so this would go to H+. But remember, H+, I should have quotation marks around it. I'm just too lazy to write H3O+, or most chemists. Most chemists are too lazy to write it all the time. So they just assume everybody knows it already. So there should be no confusion. And so this is trying to show it in equation form. In equation form, this long arrow means this side is favored. This short arrow means just a little bit happens. So what we're trying to show here is that mostly it stays together as intact molecules, and a small fraction of these actually dissociate. And that small fraction is like less than 1%, 1%, less than 1%. This is a tiny fraction. It depends on the strength of the acid. And so this is why, in general, people just say partially dissociates. No real significant degree there. Now, I talked about hydrolysis. In Chem 1B, though, we do this as hydrolysis because the next step is, this proton is going to attack water, or water is going to attack this proton, right? And so, in Chem 1B, we would write this differently. We'd write these all as hydrolysis reactions. And so, in Chem 1B, you would have written it like this. We would take our arsenic acid plus H2O. This is going to yield straight to hydronium. Hydronium plus dihydrogen oxygenate. Now formatting, I don't want it subscript and superscript. It'll take me too long to do that. And so here, this is hydrolysis. This is H2O liquid. All these are aqueous. Aqueous, liquid, aqueous, aqueous. But essentially what we have here is, these two equations are saying the same thing. It's just this one takes a lot less space than this one, so this is kind of preferred. But this is more accurate. Alright, so weak acids. And then I need to go down one level. Someone know how to do that? I'll go down one level. Oh, there. That's how I go down one level. Weak acids, and then we have weak bases. How do you know what the weak bases are? Yeah, you look at the table. And so we consult the chart. I don't, there are a lot of strong bases. I don't expect you to have them all memorized. The strong acid, yes. But you should know, when some people, when you ask them what a strong base is, they'll say sodium hydroxide. But is that it? No, that's not it. And so one of the weak bases that we can consult the chart is ammonia. And so what weak bases do is they partially hydrolyze water. And so if we look at ammonia, NH3, ammonia and water, H2O, we end up with partial hydrolysis here. So I'm going to copy these. So, what do bases do? Bases are proton acceptors. In other words, bases try to take the proton from water. And so I have ammonia here. What it's going to do is it's going to try to attack water. But this is going to be quite a struggle for ammonia. In fact, water is the more powerful. More powerful in the way that it's going to prevent ammonia from attacking. Less than 1% will be successful in attacking. And so when ammonia is successful, it forms NH4. So the charge is going to be positive because it's taking a proton. And so it's going to form ammonium and, we're going to be left with hydroxide. Now the difference between a weak base and a strong base is the amount of hydroxide that's generated. In a weak base, we don't generate that much hydroxide. In a strong base, we generate a lot of hydroxide. The same thing, the difference between the weak acid and the strong acid. A weak acid doesn't generate much hydronium. A strong acid generates a lot of hydronium. So that's ammonia. This is why remember we were doing some metathesis reactions last week. Some of you missed a lab last week, but we'll try to make it up this week. If you missed last week's lab, you could do double lab Thursday. But remember you saw ammonia, so you thought, what ions does ammonia have? Because we're looking for favorable ion combinations. In metathesis reactions, we always look for favorable ion combinations. Well, this is where the ions come from. Because ammonia attacks water. Because ammonia attacks water, we form some hydroxide ions and some ammonium ions. And these hydroxide ions, ammonium ions, can react. And so even though, yeah, there are no ions here, we got to remember ammonia is a weak electrolyte. Weak electrolytes partially react, and what forms are ions. And those ions can undergo metathesis reactions. So, for example, what cations does hydroxide like? Hydroxide likes all cations. It'll precipitate with all cations except for group 1, ammonium. Group 1 in ammonium and calcium, strontium, and barium. Calcium, strontium, and barium. And so, again, if you're looking for stuff to study, get those memorized. For sure, we're going to be using those. And so hydroxide will attack iron 3, yes. Will attack lead 2, yes. Will attack magnesium. Will calcium attack magnesium? I mean, not calcium. Hydroxide attack magnesium? Yes. In fact, it will attack the whole periodic table of cations and form precipitates, except for group 1, calcium, strontium, barium, and ammonium. That's it. Every other cation here will precipitate out as a hydroxide. Some of these, like nickel hydroxide is green, copper hydroxide is blue, zinc hydroxide is white, iron hydroxide is yellow, orange, rust, manganese hydroxide, I forgot the color, chromium hydroxide is purple, manganese, pink, I think it is. Yeah, pink, or manganese 2 hydroxide is pink. Manganese 3 is a different color. Well, anyway, it will precipitate out lots of hydroxides. So when you add ammonia to a solution that contains cations, metal cations, then you gotta watch out, lots of hydroxides. Is ammonium very reactive metathesis? We learned this yesterday. Is ammonium very reactive for metathesis reactions? Not at all. No. Group 1 and ammonium salts are all soluble. So it's the hydroxide where, as far as metathesis goes, it's the hydroxide. There are some other weak electrolytes that partially dissociate. These would be some heavy metal salts, like lead-4 chloride, or some of these other ones. You know, lead-4 chloride. When you get to heavy metal salts, the heavy metal salts would be, these are called the heavy metals here, like lead, thallium, mercury, gold. These are all heavy metals. Even silver is considered a heavy metal. Silver is not that. Well, these heavy metal salts, some of those are weak electrolytes. And so you have to be careful. But, I'm not going to get into it because that's more Chem 1A. Chem 1A, I'd get into it. I'm not going to talk about it. And so, okay, those are the weak electrolytes. The weak electrolytes on this slide. Let me just finish up with non-electrolytes and then we'll go on a break. The non-electrolytes, we say, is everything else. So, for example, let's do glucose. We do glucose, C6H12O6. Is glucose soluble? Well, you need to know the structure of glucose, but it turns out these sugars are all soluble in water. These are carbohydrates. Carbohydrates, one way to recognize a carbohydrate is the ratio. Take a look at the ratio, the hydrogen to oxygen ratio. Not 1:1. Oh yeah, 1. So anyway, it's H2O ratio. So carbon, hydrate, carbohydrate. So those are water soluble. So those dissolve. But when they dissolve, do they split up into ions or do they stay together? They stay together. So this would be a non-conductor. So if this were solid, glucose dissolved in water, so it could go aqueous, right? Let's go. So this dissolved in water, that's solubility, that's not electrolyte. Electrolyte is what happens once it's dissolved. What happens once it's dissolved is nothing. It just stays as molecules, and these molecules just float around with all the water molecules. And so it's non-electrolyte. Now, I want to note one distinction. For strong bases, we must distinguish between solubility and so, for example, if I had sodium oxide, it's not sodium oxide, let's go sodium. What's the formula for sodium oxide? Na2O. It's a solid. The first question I ask is it soluble? Is sodium oxide soluble? Well, it's group 1. Group 1 salts are soluble. And so it goes to Na2O8Q, so it dissolves in water. Then I ask myself, what happens when sodium oxide dissolves in water? When sodium oxide dissolves in water, is it going to dissociate completely, partially, or not at all? And then I ask, what is sodium oxide? Is sodium oxide a strong base, or is it a soluble salt? It's a soluble salt. What do soluble salts do? They dissociate or ionize completely. And so it's a soluble salt, meaning it's going to ionize into what? Yeah, and so the first part is we're going to form sodium ions and oxide ions. How many sodium ions do we form? 2. So we write the 2 in the front. And so it's 2 sodium ions, like this, plus an oxide ion, so O2 minus. Good. And so the first step here is it's a soluble salt. Soluble salts ionize or dissociate completely. When I say completely, or I should qualify it, completely or near completely. A little bit of asterisk there. All right, it's a soluble salt, so we're going to split it up into ions. But we know something about oxide. Oxide should have registered. This is why it's so important to know the table. You should have seen, oxide should ring a bell. What rings a bell about oxide? One of its chemical properties. One of its chemical properties is hugely significant. What is it? It's a strong base. And strong bases are too strong to exist in water. And so oxide is going to attack water. And so O2 minus will attack water. We call attacking water like this, what do we call that? Hydrolysis. So what do strong bases do? They hydrolyze water completely to form, well, hydroxide, and hydroxide. Or in other words, 2 hydroxide. I didn't have to write it separately like this, but I wrote it separately because this oxide takes the hydrogen to form hydroxide. This water loses the hydrogen to form hydroxide. So there's an ord, which just equals 2 hydroxides. We write the 2 in the front like this. Balance. This is called balance. This is what we call a strong. So we had 2 strong electrolytes. The first strong electrolyte was a soluble salt. The second strong electrolyte is a strong base. And so we say strong bases. Strong bases hydrolyze completely. Well, the sodium's still there, you know. We had 2 sodiums, but before there were 2 sodiums and an oxide. Now there are 2 sodiums with 2 hydroxides. So we form 2 sodium hydroxides. And so this is what I mean by distinguishing between salt versus base. The first strong electrolyte was the salt. The second strong electrolyte is the base. Did everybody get that then? All right, we'll take a break now and then we'll start again. The break.